In a previous room of this module, we learned about basic of computer architecture and assembly language. While those topics are essentially building blocks to learning malware analysis, we will start analyzing malware starting from this room. Prerequisites. Before starting this room, it is recommended that you complete following rooms: Intro to Malware Analysis, x86, Assembly Crash Course, x86, Architecture Overview. First step in analyzing the malware is generally to look at its properties without running. This type of analysis is called static analysis, because the malware is static and non-running. We will cover basic static analysis in this room. In particular, we will cover the following topics: lab setup for malware analysis, searching for strings in malware analysis, fingerprinting malware analysis through hashes, signature-based detection, mechanisms extracting useful information from PE header. So without further ado, let's move on the next task to learn about settings up a malware analysis lab.
Basic precaution for malware analysis. Before analyzing malware, one must understand that malware is often destructive. This means that when malware is being analyzed, there's a high chance of damaging the environment in which it is being analyzed. This damage can be permanent, and it might take more effort to get rid of this damage than the effort made to analyze the malware. Therefore, creating a lab setup that can withstand the destructive nature of malware is necessary. Virtual machines. A lab setup for malware analysis requires the ability to save a state of machine, snapshot, and revert that state whenever required. The machine is thus prepared with all the required tools installed, and its state is saved. After analyzing the malware in that machine, it is restored to its clean state with all the tools installed. This activity ensures that each malware is analyzed in an otherwise clean environment, and after analysis, the machine can be reverted without any sustained damage. Virtual machines provide an ideal medium for malware analysis. Some famous software used for creating and using virtual machines includes Oracle VirtualBox and VMware Workstation. These applications can create snapshots and revert to them whenever required, making them well suited for our malware analysis pursuit. In short, the following steps portray the usage of virtual machines for malware analysis: create a fresh virtual machine with new OS install. Set up the machine by installing all the required analysis tools in it. Take a snapshot of the machine. Copy download malware samples inside the VM and analyze it. Revert the machine to the snapshot after the analysis completes. Following these steps ensures that your VM is not contaminated with remnants of previous malware samples when analyzing new malware. It also ensures that you don't have to install your tools again and again for each analysis. Selecting the tools to install in your malware analysis VM can also be hectic. One can use one of the freely available malware analysis VMs with pre-installed tools to ease this task. Let's review some common malware analysis VMs most popular among security researchers. Flare VM. The Flare VM is a Windows-based VM well suited for malware analysis created by Mandiant, previously FireEye. It contains some of the community's favorite malware analysis tools. Furthermore, it is also customizable, i.e., you can install any of your own tools to the VM. Flare VM is compatible with Windows 7 and Windows 10. For a list of tools already installed in the VM and installation steps, you can visit the GitHub page or Mandiant blog for the VM. Since it is a Windows-based VM, it can perform dynamic analysis of Windows-based malware. An instance of Flare VM is attached to this room for performing practical tasks. Please click the Start Machine button on the top right corner of this task to start the machine before proceeding to the next task. The attached VM has a directory named Mal on the desktop, which contains malware samples that we will be analyzing for this room. RENUX. RENUX stands for Reverse Engineering Malware Linux. It is a Linux-based malware analysis distribution created by Lenny Zeltser in 2010. Later on, more people joined the team to improve upon the distribution. Like the Flare VM, it includes the most popular reverse engineering and malware analysis tools pre-installed. It helps the analyst save time that would otherwise be spent identifying, searching for, and installing the required tools. Details like installation and documentation can be found on GitHub or the website for distribution. Being a Linux-based distribution, it cannot be used to perform dynamic analysis of Windows-based malware. RENUX was previously used in the intro to malware analysis room and will also be used in the upcoming rooms. Please click the Start Machine button on the top right corner of this task to start the machine before proceeding to the next task. The machine will start in a split screen view. If the VM is not visible, use the blue Show Split View button at the top right of the page. The attached VM has a directory named Mal on the desktop, which contains malware samples that we will be analyzing for this room. Alternatively, you might use the following information to log into the machine. Machine ID.
Check this one. In the intro to malware analysis room, we identified that searching for string is one of the first steps in a malware analysis. A string search provides useful information to malware analysts by identifying important piece of string present in a suspicious malware sample. To learn a small bit of information about string, we can look at this room dedicated to strings. How does string search work? A string search looks at the binary data in the malware sample regardless of its file type. It identifies sequences of ASCII characters or Unicode characters followed by null characters. Whenever it finds such sequence, it reports that it is a string. This might raise a question that's not sequences of binary data that looks like ASCII or Unicode characters will be actual strings, which is right. Many sequences of bytes can fulfill the criteria mentioned above, but not string of useful value. Rather, they might include memory addresses, assembly instructions, etc. Therefore, a string search leads to many false positive FPs. Those FPs shows up as a garbage in the output of string search and should be ignored. It is up to the analyst to identify the useful strings and ignore the rest. What to look for? Since an analyst has to identify actual strings of interest and differentiate them from the garbage, it is good to know what to look for when performing a string search. Also, a lot of useful information can be unearthed in the string search. The following artifacts can be used as an indicator of uncompromised IOCs and proved more useful. Windows functions and APIs like set, Windows hook, create process, internet open, etc. They provide information about the possible functionality of the malware. IP addresses, URLs, or dynamic can provide information about possible C2 communications. Command and control infrastructure are set of program used to communicate with the victim machine. These comparable to reverse shell, but generally more advanced and often communicate via common network protocols like HTTP, HTTPS, and DNS. The WannaCry malware's kill switch domain was found using the string search maliciousness. Strings such as Bitcoin addresses, text used for message boxes, etc. This information helps set the context for fuzzy malware analysis. Basic string search. So we have the desktop, user administrator, desktop, string to binary. So we learned about the string utilities such as pre-installed in Linux machines and can be used for basic string search. Similarly, the Flare VM comes with Windows utility strings. Flare VM comes with utilities string. I guess we will find it somewhere here. No, we don't. Okay. Maybe floss. So strings. So if I will wish to go in here and open cd strings. Oh, what a nice surprise. Pass to the binary. So strings 1. We have all the strings that files 1 has. Binary search. So performs same task. The Windows utility is part of the internal suite. Sysinternals, a tool published by Microsoft to analyze different aspects of the Windows machine. Details about the Strings utility can be found in documentation. We have the suite. Let me return to this one real quick. Utilities. These internals, and we have strings in here. Yeah, we have. So, these utilities can pre-install in the Flare VM attached to this room. The good things about the command line string utility is that it can dump strings to the file for further analysis. In the attached VM, executing forward command will perform basic string search in a binary. Several other tools included in Flare VM can be used for string searching. For example, Cyberchef has recipe for basic string search as well. PS Studio we all know this. PS Studio. So PS Studio Flare utilities PS Studio. Let me real quick open the file. Real quick. It's not too quick. Take your time, take your time. Desktop mode 1, and we have all the bells and whistles. Strings. And we have all the bells and whistles of string searching here. I guess it is. IP address. This one. Okay. So, PS Studio also provides additional information about the strings like encoding size 11. Here we have encoding size of. Let me copy the value. See what we got in here. Okay. I guess we'll found the gibberish, but maybe not that gibberish. So, size, where the string was found, and hint to guess what string is related to. It also has a column of blacklist which matches string against some signatures. Blacklist. Okay. We have blacklist in here. Get priority. What? Priority class. Set console node. Raise exception. Get thread ID. Write the file. Okay, write the file. Very nice. Indicators. Suspicious. URLs. Okay. Looks very suspicious from my point of view. Let me details. Go to the details one. Oh, have in here blacklisted functions, I guess. Get current process ID, device control, terminate process, get current thread, open process, delete file, find first file, okay. So the above screen for the PE Studio shows strings found PE Studio in the malware sample. It can be done by selecting strings. On the left pane we have in here strings. So blacklisted here shows the bunch of window API calls which PE Studio flags as a potential used malicious process. You can learn about them in API. Let me check this one real quick. We have mal API IO, and we have really nice list of functions that can be used in a malware. So, obfuscated strings. Searching for strings often proves one of the most effective first-step malware analysis, as seen in case of WannaCry. Effective use of string search can often destroy malware propagation and infection. The malware authors knows and do not want simple string search to throw their malicious activity. Therefore, they deploy techniques to obfuscate strings in their malware. Malware authors use several techniques to obfuscate the key part of their code. Those techniques often render string search ineffective. We won't find much information when we search for strings. Mandiant launched Floss to solve this problem. Surefire Lab obfuscated string solver. Floss uses several techniques to deobfuscate and extract strings that would not be otherwise found using the string search. The type of string Floss can extract, how it works. Mandiant blog. This is the blog automatically extracting obfuscated strings from malware using the Fire Labs obfuscated string solver Floss. So we have in here. Okay. Let's return to our no static strings. Okay. Let me real quick search for this one. What? So, Floss. Do we have it? Yeah, we do. Okay, so Floss. No static strings. Strings if I can type. Let me see. Do we have something in here? Please remember that command may take some time to execute and may see what appears to be some error message before results are generated. Okay. So now we wait. No static. Use flows to identify obfuscated string found in examples 2, 5, and 6. Which of those symbols contain the string debug view exe? It takes some time. Okay, I will return. After there is some result in here, I guess. So, or maybe I will try to do this. Floors. No static. Strings. 2. Error. No static. No static strings. String. If I can type. Okay. Nothing in here. Very well. Type. I guess the first one still working. Okay. Nothing in 5. Also 6. Oh, we have it. We have code flow pass of code. Oh, the warnings that we were told. Let us see. Float beside string. Decoded one string. AD. That's it. I will return with the results. And so we back again. And we have the DBG view. So 6 will be the answer. Very well. Let me proceed as the first one. And nothing has happened. Well, it's too big. Well, in memory. So, fingerprinting malware. When analyzing malware, it is often required to identify unique malware and differentiate them from each other. File names cannot be used for purpose as they can duplicate easily, might be confused. Also, file can be changed easily as well. Hence, the hash function is used to identify malware sample uniquely. A hash function takes file data of arbitrary lengths as input and creates fixed lengths unique output based on file content. This process is irreversible as it cannot recreate a file content using the hash. Hash function had a very low probability, practically zero, of two files having different content but same hash. A hash remains same as long as file's content remains the same. However, even the slight change in the content will result in different hash. It may be noted that the file name is not a part of the content, therefore changing the file name does not affect the hash of the file. Besides, the identifying files hash are also used to store password to authenticate users. In malware analysis, hash file can be used to identify unique malware. Search for these malware is in different malware repositories and databases, and as an indicator of compromise. Commonly used methods of calculating file hashes for identification of files. A hash of complete file is taken. There are various methods to take the hash. Most commonly used methods are MD5 sum, hash1 sum, SHA-1 sum, SHA-2 56 sum. The first two types are considered insecure or prone to collision attacks when two more inputs results in the same hash. Although the hash attack for those hash functions is not very probable, it is possible. Therefore, SHA-256 sum is currently considered the most secure method of calculating the file hash. In attached VM, we can see multiple utilities calculating the file hash for us. So we have the indicators. I guess. Nope. This is it. MD5, SHA-1, SHA-256. And we have entry point, no. Another scenario, finding similar files using hashes. Another scenario in which hash function help the malware analysis is identify similar files using hashes. We already established that even the slight change in the content of the file could result in a different hash. However, some types of hashes can help identify the similar among different files. Let's learn about some of those. Imp hash. We have imp hash. That is it. Imp hash stands for import hash. Imports are functions that an executable file imports from other files or dynamically linked DLLs. The imp hash is the hash of the function calls libraries that malware sample imports and asks which those libraries are present in a sample. This helps identify samples from same through the groups or perform similar activities. More details on this imp hash can be found in this blog. See real quick. Google Cloud track malware with import hashing. And we have in here the, I guess, code for this one. All the import hashes. So we have in here all the import tables. And then we hash them. Very clever. I guess good time we're living in. So we can use the eStudio to calculate the imp hash of the sample we have in here. The imp hash. any malware samples with the same import hash in the same order will have the same import hash. This helps in identify similar samples. So we have in here SHA, different SHA-256 hashes, but the same imp hash. So those edges are the same, I guess. This is it, or similar in their behavior. Very nice signature. Hey, Odo. So, in the debug screen malware bazaar, all the examples have same imp hash. We can see that all these samples are classified as the same malware family. We can see that the SHA-256 hash is vastly different. It does not provide any information as to their similarity. However, the same imp hash helps us identify that they might belong to the same family. Fuzzy hashes SS-deep. Another way to identify similar malwares is through the fuzzy hashes. A fuzzy hash is a content-triggered piecewise hash. This hash is calculated by dividing a file into pieces, dividing file into the pieces and calculating the hash of the different pieces. These methods create multiple inputs with a similar sequences of bytes. Even though the whole file may be different, more information on SS-deep can be found on this link. Let me see real quick. This is an introduction to SS-deep. Is program for computing context-triggered piecewise hashes. And we have all the contributors and everything. Quick start. So we have tar-zip. Then we are making this one, and then SS-deep still install. Okay. Error message. Okay. So we have SS-deep, one block hash, very. Multiple utilities can be used in an attached VM to calculate SS-deep. Do we have SS-deep in here? I don't think. SS-deep. So we have the SS-deep in here somewhere. Let me SS-deep. SS-deep exe. Let me see this one real quick. Here we go, SS-deep. So we have maybe if I will get this one to mold, this will give me, oh, very well. We have the SS-deep of all the files that we have in mal folder. We can try other options shown to help per requirement. When we have the SS-deep hash, we can match those hashes together to identify similar files. This helps us to identify similar files if we have a bulk of data. The documentation link provided above has very good examples of this. The following terminal window shows one of them examples relevant to our use case to match the file. Can use a D operator or R operator runs recursively, and L, I guess L uses relative paths for their files. So we have this one. Do we have similarities? We don't have similarities. The same located. The samples located in the directory touched sample have in as file 3. What? Which of samples have the same imp hash as file 3? Let me. How do I get imp hash? Matches known signature DD class recursive use compare signature files. Let me see how do I get the imp hash. But from, I guess, where rec. What's rec? Disk load to, I don't know, hash. Let me real quick fetch hash. Chelsea internal suit. Portable executables. Written. Which one? BE something. BE something. Let me see. Pokemon PE. I guess we have B. Password PS service RAM. Sysmo. Sysmo potential. Sysmo impact. Maybe I think it can get me this one. Let me see. We have Python in here. Python in the house. Import PE file. Yes, we have this one. File. PE. I need to read this one and then get hash. File 1. P. File PE. No. 1. one get in hash d in hash. We have it. Wait a minute. Do I? Wait, let me see this one real. I guess I will take the visuals to the panel for this one real quick. This is it. This is it. If oh yes, oh is fine. Voice us join join let me see now. Oh, oh, fine. F fine. Fine. Yes. We have fine. EE fine. F5. This one, ring. Now we need to find the duplicates. So, I guess C set. Now 4 E F E C otherwise duplicates append B L C and now point original and duplicate. Now let me see where I am. Terminal PowerShell, or do I need command prompt, the regular one? Let me desktop this one. Now I need to save this one. So into the desktop. source C. Find duplicates. Now, let's see. You cannot run this one. What? It's not working. Let me see. So, 3 is not needed. Addition trunk. Wait, what? All? Nope. Okay. Unicode code cannot. It is. Specify to one. Oh, this thing cannot find specified. Wait, what? Desktop mode 1. Cannot find specified. Wait that. Pause. System cannot find 1. Let me check this one real quick. See. Import OS. List. Here. No. Oh, dude, why? I don't understand this one. Successfully updated. Was I inactive? So after some time, reads the script that can find to imp hashes that are duplicates. There you are. Here's a file 3. So file 3 and file 1 are duplicates, and file 2 and file 5 also are duplicates. Using the deep utility, what is the percentage match of above mentioned files? So let me see real quick. How do I get this percentage? For the H loop, H, yes, percentage, pretty prints duplicates, directory pretty simply. It's all recursive silent. Let me see. Where do we have the percentage? Let me check this one real quick. The percentage. With me. So file loads, compute matches, book, file enabled, loads when score is greater than value threshold. Okay, I guess I need to do some research. SSD percentage. Oh, D. L. What is L? Enables relative absolute flags. What is D? D, I guess. Directory, I guess. Computes, news, score. Okay. Let me see. L, R, D. 23. Very nice. 3 matches, so 1. Signature-based detection. In the previous task, we learned how hash could identify identical files. We also found out that hashes can be changed by changing even the single byte of the date in the file, and how specific hashes like imp hash and deep SSD help us identify the similarities, while using imp hash and SSD provides a way to identify of some files are similar. Sometimes we just need to identify if file contains the information of the interest. Hash are not the ideal tool to perform this task. Signatures. Signatures are a way to identify the particular file has a particular type of content. We can consider a signature as a pattern that might be found inside the file. The pattern often a sequence of bytes in a file with or without any context regarding where it is found. Security researchers often use a signature to identify patterns in a file. Identify if a file malicious and identify suspect behavior and malware family. Yara rules. Yara rules are a type of signature-based rule. It's famous called pattern match Swiss Army knife for malware. Researchers Yara can identify information based on binary and textual patterns, such as decimal and strings contained within a file. TryHackMe has dedicated route for Yara rules if it interests you. The security community publishes a report of open source Yara rules that can use per your needs. When analyzing malware, we can use repository to dig the community's collective wisdom. However, while using those rules, please keep in mind that some might depend on context. Some other might just be used for identification of patterns that can be non-malicious as well. And this because a rule hits does not mean the file is malicious. For better understanding, please read the documentation for the particular rule to identify the use case where it will be applicable in best possible manner. Proprietary signatures, antivirus scans. Beside the open rule signatures, companies spend a lot of resources to create proprietary signatures. The advantage of these proprietary signatures is that since they have to be sold commercially, they are lesser chance of false positives when signature hits in non-malicious files. However, this might lead to a few false negatives when a malicious file does not hit any signature. Antivirus scanning helps identify the file is malicious with high confidence. Antivirus software will often mention the signature that the file has hit, which might hint at the false functionality. However, we must know that despite the best efforts, every EV product in the market has some false positives and some false negatives. Therefore, when analyzing malware, it is prudent to get the verdict from multiple products such as VirusTotal website makes this task easier for us. When we can find this verdict about the file from 60 plus AV vendors, apart from some very useful information, we also touched upon the topic in our intro the malware analysis room. Please remember, if we are analyzing this sensitive file, the best practice is to search for hash on VirusTotal or other scanning website instead of uploading the file itself. This is done to avoid leaking sensitive information on the internet and letting the sophisticated hacker know that you are analyzing their malware. Since we have covered Yara rules in the details in the Yara room and VirusTotal scanning, In the intro malware analysis room, we will not cover them again. However, the Flavium has another very cool tool that can be used for signature scanning, Kappa. Another open source tool created by Monday, and this tool helps identify the capabilities found in PE files. Kappa read the files and tries to identify behavior of the file based on signatures such as inputs, strings, mutex, and all the artifacts presented in the file. For further detail into the background of Kappa, we can visit GitHub page and Mondian blog post introducing Kappa. Do we need? I guess we do if we are using this one. Oh, Kappa. Defense, evasion, obfuscated file information. Very, very nice too. Kappa Explore Web. And here we go. Automatically identify malware capabilities problem that we have created. Process A, create mus A. So now interesting string. Oh yes, it is interesting. Create mux TCP socket. So we are going to sleep, create process, and communicate socket, receive, send TCP. Very nice. Let me see. So now we can Kappa malware exit. So let me see where the Kappa is located. In here, Kappa analysis. Nothing is there. GitHub using the hacker Kappa sample. Where do we have this Kappa thing? Malware blob. Nope. Nope. Dude. Maybe Mandiant, Forensic, nope. Flare. Debugers, Flare. Kappa. Let me see. Kappa. H. Maybe we have privilege. Oh yes. So we have this Kappa thing in here. Let me run this on the first one. Dear Kappa 1. Oh yeah. Analyzing the program. So detailed. We can hit it with the rules. Where do I have the rules for this one? Zoom out there, and we have this really nice table. We can see that Kappa has mapped identified capabilities according to the MITRE attack framework and malware behavior catalog. What is catalog for? Malware behavior catalog version 3.1 MBC. Behavior, micro behavior techniques, Looks good, looks good, looks good. So we have this one. Now let's use Kappa analyze these 4 answer following questions. Why did I write it for that one? Oh, this looks even better in the real life. So let me analyze model 4. See what we got in here. How many matches anti-VM execution techniques were identified in the sample? Does the sample have capabilities to suspend and resume the thread? Yes, no answer for no. What MBC behavior is observed against MBC objective anti-static analysis? At what address is the function that has a capability check HTTP status code? Let me real quick see anti-static behavior analysis. Anti-static analysis. Anti-static behavior. Anti-static analysis. Behavioral analysis. Whoa. Static analysis. Let me see this one real quick. Just maybe I will try to add our. Nope, I cannot do that. Okay. So 4. Let me return when we have results for this one. So we have really long list of everything that Kappa found. So defense evasion system file, anti-static analysis, anti-behavioral analysis, anti-static analysis, defense evasion. So how many matches for anti-VM? Anti-VM execution techniques were found in this malware. So we are going anti-VM anti-bugging detection, anti-VM detection. 86. Okay. So now that's yes or no capabilities. Suspend, resume. Process interaction host. Process heap. Process create, terminate. Suspend, resume. Okay, yes. What MBC behavior is observed against object anti-static analysis? Let me see, anti-static analysis. disassembler, evasion, obfuscation, and then let me see one real quick. I guess what address function that has capability check HTTP status code. Address of the function. I guess I can find this one only if I open PA Studio. Open Mal 4. So we need the with this. Nope. Header. Nope. Functions, I guess. Get HTTP. Nope. Labels. Oh, here we go. No. Do. I guess try hard me need to do with this something. It's very sometimes so. So let me see this one. We have to enter for the malware number 4, malware number 5. Yes. Let me see. Create table. Start. So check HTTP. Check HTTP. File offset with this. let me this is one. What is the address? Wait a minute. Yes, I need strings. Address. Network. Collection. Can I find? Search. No, no, Google is not good for this one. Google is not good for this one. And I have missed this one. Okay. Let me try something else. Strings. 4. Results. Search. Check. Checkmate. Take HTTP. Okay. HTTP. Tag. Tag. To realize. Check, 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 check. Nope, 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 nope. Nothing. Code. Maybe. What address is the function that has capability. Function that has capability. Okay, let me see in here. HTTP. Open send. Status. Wait, what? Function with status. Going on here. HTTP. Get current directory. Get find. Get time. Get menu. Get version. Get instance. Get everything but not internet. Okay, let me check this one real quick. I guess I will try CFF. Maybe here I will get some more convenient results. Dependencies. Let me see. Resources. Directory entries. Okay. Import. Let me see. So I guess the answer is that we need to run the cap. flag. So the flags, and then sample name for basic. I will return when I have some answers or results. So let me jump to the next task while we have this one waiting. So far this room we have recovered techniques that work regardless of the type of the malware. However, those techniques are a little hidden miss, as they don't always provide us with deterministic information about the malware. The PE headers provide the more deterministic characteristics of the sample, which tell us much more about the sample. So let me return to this one real quick after we see the many information about it. Whoa. Get model handler. I guess we have share models. Not reads Rabay. Fire right. We were namespace Arthur. Michael Hanhoff. What is that have to do with questions I had? So, create or open registry reg set values. Do. Let me see PowerShell real quick. Create, maybe it is in here. I don't know. Get more handler. Get more handler. Number of names. Book or login out to start execution. Run files. Okay. Let me see this one cap. 4. I guess if scrolling is limited, then we will have this one also. Buffer size. Can I? Number of buffers. Number of buffers. So let me see if machine can get this one and not restart it over. console, baby. This access. Set hot exec. Write file. Discovery. Exec read file. Get private profile string. Get file attribute. Find first file. Get attribute. Create directory strings. Get environment string. Local. Remember. Is my reminder. What's that? Title. Get stock string. Removal. Indicator removed from the tools. Static analysis. Get cursor pulse. Matches. Okay. FS access. Debug detection. Detect being anti-software CPP. I don't see what I need. Over particle Bob. Return. Do what did these files have to do with it? Matches. Get file. Set file to remove file. Raw file. Read file. Set. Get address. Get port address. What do we have here? Function where daughter present the address. Check HTTP status code. Check HTTP status code. Function. Get ready. Listen. Let me check this one real quick. Maybe I will redirect it to the file. Let me see this one real quick. Text. Okay. We'll come back later. So I will proceed in this one. The PE header programs that run are generally stored in the executable file format. Those files are portable because they can be taken to any system with the same operating system and dependencies, and they will perform the same task on the system. So portable executables. Therefore, those files called portable executables. The files consist of sequences of bytes stored on the disk. The sequence is specific format. The initial bits define the characteristics of the PE file and explain how the rest data initial part of PE files is called PE header. Several tools, FlareVM, can help analyze PE header. Studio, one of them. We already familiarized ourselves with PE Studio in the previous task, so we will just use that in this task as well. PE headers contain rich information useful for malware analysis. We will learn about this data in the detail in the detecting PE headers. Let me see what is it. So we have results in here. In a file format, reference practical chapter 2. Here we go, yeah. So the what they ask numbers function the its address lyrics 486921. That's it for this task. So PE linked libraries, imports and functions. This room I have just finished. However, we can get following information in PE as in overview. So let me open this one. Let's see. What do we get in here? So we need the libraries. Okay. The PE does not contain all of its code to perform all the tasks. It often reuses code from libraries often provided by Microsoft as part of the Windows operating system. Often certain functions from those libraries are important by the PE file. The PE header contains information about the libraries that PE file uses and the functions it imports from those libraries. This information is very useful and malware analysts can look at the libraries and functions that PE file imports and get rough idea of these functionalities of malware samples. For example, if malware sample import create process A function, we can assume the sample will create a new process. Similarly, other functions can provide further information about this sample. However, it must be noticed that we do not know context in which those functions are called by just looking at PE headers. We need to dig deeper into that, which we will cover in the upcoming rooms. PE Studio has the libraries option in the right pane, which we selected shows us the libraries we can see. The PE file will use So we can see in here the libraries and functions. Identify the part executables. As we have seen so far, starting analysis bears a lot of information that can be used to gather malware. Malware authors understand this as a problem. Therefore, they often go to great lengths to throw analysis. One of the ways they can do this by packaging the original example into shell type code that obfuscates the properties of the actual malware sample. This technique is called packing, and result PE file is called a packed PE file. Packing greatly reduces the effectiveness of some of the malware analysis techniques we have learned about so far. For example, if we try to search for strings in a packed executable, we might not find anything useful because the packing. Similarly, searching for similar sample using SSD might return more samples packed with the same packer instead of samples behaviorally similar to the sample of interest. Some signatures might be also invaded due to the malware sample being packed. As we see in upcoming dissecting PE headers rooms, we can identify packed executables by analyzing PE header of the malware sample. The PE header contains important information such as number of sections. We have the permissions of different sections, and we can see the permissions and so on value, size of the sections, etc. This information can give us pointers to help identify the malware sample is packed, and if so, which type of packer has packed the executable. One example, desktop. Malforpes, which library is blacklisted. So RPCT4 loop, RPCT4 DLL. What does this DLL do? Who knows? Remote precision called runtime. Let me check this one, though we have finished this room. That wraps up the basic static analysis room. So far we have learned the following. Lab said helpful malware analysis. We didn't learn this. Search for strings that obfuscate the string. Yes, we do. Fingerprinting malware using hashes that identify similar files. Samples using imp hash and SSD. Yes, we do. Use signature-based detection like Yara and Kappa. Yes, we do. Identify artifacts from the PE header. Yes, we do. Thanks for this room. So long, bye-bye.